Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis taken by Professor Krishna P. Kaliappan from Department of Chemistry. Myself, Sri Lakshmi S. I am a fourth year PhD scholar in IIT Bombay in the Department of Chemistry. So, this is our sixth tutorial session. So, in the last week tutorial session, we have finished up to this week 3 assignment. I hope it's all clear. And today, we will be discussing the week 5 lectures first, and then we will move ahead with some question discussion. Before that, we will wait for a couple of minutes to see whether anybody else is joining, and we will start the session. Okay, so let's start. So far we have discussed up to week 4 lecture contents, and we have solved up to week 3 assignment questions along with some other questions as well. So, today we will be. Okay, sorry for that. So far we have discussed up to week 4 lecture contents, and we have solved up to week 3 assignments, and we have solved the related problems as well. So today, firstly, we will start with the discussion on week 5 lectures. So the first week lecture of week 5 was about longifalling. So in that lecture, we have seen the application of Michael addition and 1-2 rearrangement in Corey's total synthesis of longifalin, De-Mayo reaction and group fragmentation in Opolzer's total synthesis, and polyene type cyclizations in Johnson's total synthesis. So, three total synthesis have been discussed for this longifalin. So, longifalin, the structure is given here. So, that is basically obtained from the pine resins as an oily liquid hydrocarbon, and it is a tricyclic compound as we can see from the structure with three chiral centers 1, 2, and 3. And no functional group other than the double bond. So this double bond is the only functional group present in this longifold. One second, let me make sure this is getting recorded. Yeah. So it is a tricyclic compound with two quaternary centers, three chiral centers, and no functional group other than this double bond. So the first total synthesis was done by Corey's group, E.J. Corey's group in 1964, where he have completed this total synthesis in 15 steps with 2.4 percentage overall yield. And the key steps of his total synthesis included pinacol rearrangement for ring expansion, where he used this Whelan-Miescher ketone as the starting material, and they have also utilized an intramolecular Michael addition reaction for this completing this total synthesis. Now, for Opolzer's total synthesis, which was done in 1978, it was completed in 11 steps with 23% of overall yield, and he used 2 plus 2 photocycloaddition, that is intramolecular 2 plus 2 photocycloaddition using cyclopenadiene carboxylic acid as the starting material. And other key steps of this synthesis involve stockinamine acylation and group fragmentation. Now, in Johnson's total synthesis, which was completed in 1978, he completed this total synthesis in 11 step with 26.6% of overall yield. So, this was a serendipitous approach, and this main key step was Lewis acid mediated cyclization, which is a polyenes type of cyclization. So, here in this method, he is using only one step for the formation of a tricyclic compound, and the starting material used by this Johnson's group for completing the total synthesis cyclopentanone. So that was about longiflorin. Then coming to the next molecule, which was carpenone. So in this carpenone total synthesis, we have seen the application of intramolecular Diels-Alder reaction and oxidative phenolic couplic reactions in the total synthesis of carpenone by O.L. Chapman. And carpenone is a lignin. The structure is given here, which is obtained from the bark of carpeno tree. So it is having like three the six membered ring, then two five membered rings are there, and with this one pyran kind of ring system. So basically, four six membered rings are there, and it is having five contiguous stereogenic centers. So this Chapman's total synthesis was completed in 1971, which was a Diels-Alder cycloaddition and intramolecular Diels-Alder cycloaddition and oxidative phenolic coupling as the key reactions. So here he have used type 1 intramolecular Diels-Alder reaction, which results in the formation of this kind of bicyclic, fused bicyclic system. Dienophile is attached to the carbon 1 of the di. Now, in type 2 intramolecular Diels-Alder reaction, which is not being used here, but in type 2, basically it results in the formation of bridged bicyclic system, provided that the ring form should be larger than 6 membered, and where the dienophile is attached to the C2 atom of the di. Then we have seen what is oxidative phenolic coupling, how it works under palladium catalysis, palladium condition, then Claisen rearrangement. So this was basically a biomimetic route which he took four steps to complete the total synthesis with 46% of overall yield. And the starting material used in this total synthesis was 2-allyl 4,5 methylene dioxyphenol. Now, for the total synthesis, which was completed in 1981 by Matsumoto's group, they used a copper 2 saline complex for the phenolic coupling rather than palladium. And their approach made use of the oxidation of trans 2,1 propenyl 4,5 methylene dioxyphenol with molecular oxygen in the presence of transition metal complex, and they completed this total synthesis in a single step with 90% of yield. So, that was the two total synthesis which were discussed for this carpenone. Okay. Now moving on to the next natural product, which was about Mavinolin, where we have seen the application of an annulation method based on experimental modification of McMurray process for the total synthesis of this plus Mavinolin by Cleve et al. So, Mavinolin is a fungal metabolite and which is useful as metabolic props for studying cholesterol homeostasis and their potential value in treating cholesteremic individuals. And it is characterized by this hydroxy six membered lactone ring with 8 chiral centers in total and a cross conjugated diene. And these are the major challenges associated with this natural product also. So in Cleve's total synthesis, which was done in 27 steps with 1.27 percentage of overall yield. So in this total synthesis, they have basically used this Evans chiral auxiliary for generating this 8 chiral centers present in this molecule, and then they have utilized this McMurray coupling to introduce the double bond, and then diene plus Evans chiral auxiliary for an asymmetric Diels-Alder reaction. And this is basically a convergent synthesis using 3 different fragments, and they used Evans auxiliary and malic acid as the starting materials. And the key steps of this reaction involves this asymmetric Diels-Alder reaction, iodolactonization. Then they have used Wilkinson's catalyst for decarbonylation and Fettison's reagent for converting lactol to lactone selectively. And they have completed, as I said, this total synthesis in 27 steps with 1.27 percentage of yield starting from the chiral auxiliary. Now, for the next lecture, we have seen the total synthesis of gibberellic acid. So, there we have seen the application of iodolactinization in the total synthesis of gibberellic acid by Corey's group. So, it is a plant hormone belonging to gibberellins, and it is having 8 stereo centers, molecular complexity, centers of high sensitivity towards many reagents. And these are the major challenges for the total synthesis of this natural product. Now, in Corey synthesis, we have seen intramolecular Diels-Alder reaction, iodolactonization, epoxylactonization, radical cyclization, and Claisen rearrangement were the major steps used. And the starting material used was cyclopentadiene, and we have seen a discussion about what is iodolactonization and how the key intermediate is prepared via four pathways. And they have not used they have also used heterodyl reaction as well, but this order synthesis is not completed up to the intermediate. We have seen in the lecture. Now, this is the pinacol rearrangement, which we have seen already in the lecture. So, this is pinacol means this kind of a diol. So, in the presence of a sulfuric acid or any other acid, one of this hydroxyl group get protonated. So, now this act as a living group, and one water molecule will leave to form this carbocation. So, this carbocation, what will happen is this methyl group from the adjacent carbon will migrate to this position, so that a carbocation is formed at the center. So this is basically more stable cationic intermediate. So the major driving force for this migration is the formation of more stable carbocation. Now again, what is happening? This like H2O will take this proton and it will form this kind of intermediate. So this is known as pinacolon. So this pinacol, a loose of water molecule, and this migration of methyl group is taking place to form this pinacolon as the final product. I hope this is clear. Pinacol rearrangement. Now we will see what is wheel and Miescher ketone. So wheel and Miescher ketone, previously I think we have discussed about hydrosparish ketone. So instead of that cyclopentane, we are taking the cyclohexanone derivative, and this methylvinyl ketone. We will be getting this type of intermediate after this Michael addition. Then as proline mediated this aldol reaction, aldol condensation would happen to form this 6 fused membered ring with this methyl group over the center, and alpha beta unsaturated ketone here, and here one ketone. So this is wheel and Miescher ketone. So based on the proline derivative we are using, that is s proline or the r proline, we can control the stereochemistry of the methyl group at this junction. So that is known as wheel and Miescher ketone. Now we will see what is stock enamine synthesis used for alkylation, acylation, and conjugate addition. So the secondary amine and the cyclohexanone or any ketone under mild acidic condition can give this enamine. So which act as a temporary activator. So this nitrogen lone pairs can come over here, and if it is attacking over this uh, like carbonyl compounds, it can form this kind of intermediate, and then that can be hydrolyzed to form this type of compound. Or if it is attacking on alpha beta unsaturated compound at this fourth position, it can form this, and then hydrolysis will remove this and form this ketone. Then again, yeah, this is actually R. Okay, this is some mistake, so we'll just leave this. So this can be used as the corresponding source to this can attack on this electron deficient centers, and hydrolysis will remove this secondary amine, and we will be getting the ketone as the product. So that is known as stoichionamine synthesis for alkylation, acylation, and conjugate addition. Now the next reaction was group fragmentation. So there what is happening, this type of a compound would be there. So alcohol, and towards this alpha beta, this position bromide is there. So this tertiary butoxide or any base can take the proton of this alcohol, and this bond will shift over here, and this bond is breaking and it is shifting over here, and this bromide is leaving. So that will give this compound, which can be written like this. Then again this Br minus will attack over this center, this double bond, then will go and attack over this, and this will migrate to here. So that will form this one. Then again this minus charge will come over here. This bond is breaking, and this Br minus will be okay, will be leaving to form this one. So the two different pathways it is shown here. So this type of compound will be the resulting. So OH minus, that proton will be taken by a base, that bond will come over here, this bond will this ring will open, it will come over here, and this bromide will leave to give this compound, that is known as group fragmentation. Now about this oxidative phenolic coupling. So here what is happening, this type of radical is forming from this phenol. Then it can combine to form this kind of compound which can be tautomerized to form this biphenol kind of system. Like so this is radical pathway. Now radical phenolate pathway means one of this radical and one of this will be in phenolate form, and that will combine to form this radical, then electron will remove and tautomerization to give this. Then it can be either through radical nucleophilic pathway also or radical phenoxonium ion pathway. So these are the four different pathways for oxidative phenolic coupling. I'll give you some time to quickly go through this all: radical phenolate, radical nucleophilic, and radical phenoxonium. Okay, now moving to the next reaction, which was about this Evans type of chiral auxiliary. So there what is happening, this type of chiral auxiliaries are used which can react with aldehyde, either this type of intermediate or this type of intermediate. So based on the type of intermediate we can get Evans syn product, or non-Evans syn product. So here we can see there is a coordination, like arrangement is different as compared to this one. So that's what is giving evansin and non-evansin. So we can control the stereochemistry of the reaction based on the, which is basically will be controlled by this benzyl group. So according to that we can get the desired product which we want by changing the stereochemistry on this Evans type chiral auxiliaries. Now about Wilkinson's catalyst. So that is basically used for the hydrogenation of alkene in the using mostly THF and tertiary butanol solvent. And here this is this Wilkinson's catalyst. So here is the mechanism. So from this Wilkinson's catalyst first the ligand dissociation is happening. So here there is one empty space. So there this oxidative addition of hydrogen will take place to get this compound. Then ligand association will take place to give this intermediate, and then 1 2 insertion is taking place where this alkene will get inserted between this hydrogen to give this product, and then reductive elimination of this and this hydrogen will take place to get back the catalyst as well as the reduced product. So this is an example for not example, this is the mechanisms for the action of Wilkinson's catalyst. Now, so in the case of 1,4 diol, 1,5 diol, or 1,6 diol, when Fittison's reagent is used, it will form lactone just like PCC. So in the case of 1,4 diol, we will be getting gamma lactone, that is 5-membered ring. In the case of 1,5 diol, we will be getting 6-membered delta lactone. And in the case of 1,6 diol, we will be getting 7-membered delta dash lactone. So this is the mechanism. This one of this will get oxidized, and that oxygen lone pair will attack over that, and that will form this lactone. So this is the Fettison's reagent, silver carbonate and silicate. So that's all about the week 5 lectures, and the week 5 lectures and the related reactions and its mechanisms we have seen. So I will give you some time to quickly go through this, and then we will move on with the question discussion. So now we will move ahead with the week 3 assignment. Week 4 assignment. So the first question is identify the major product A in the following transformation. So this cyclopentanol derivative we are using treating with this methyl vinyl ketone under S proline condition. So which will be the major product out of the four options given here? So this is an example for the what we saw for the preparation of wheel and measure ketone. And so the same thing is happening here also. This one for addition, like this is attacking, not one for addition, this is attacking over this Michael addition, and then aldol will take place to form the product. So the correct answer is option B. And this is an example for Robinson annihilation, and this product is known as Hajos Parish ketone. Moving to the second question, identify the intermediate formed in the following reaction sequence. So here, this tetraene under photochemical condition, we are getting an intermediate, which upon heating at 200 degrees Celsius, we are getting this product. So which will be the intermediate out of this four options for this reaction sequence, which will be the intermediate forming in this reaction? So here the correct answer is this one. So as we can see here, cyclization is happening. So this is coming over here, this is coming over here, and this four membered ring is forming between this two, and this is also. So uh, so firstly, this intermediate, this option C will be forming. Then again, what is happening, and upon heating, maybe we can say. Electrocyclization is again happening. Before that, this four membered ring is opening, and then electrocyclization is happening to give this product. So the correct answer is option C. Now moving to the question 3, identify the starting material in the following reaction. So this particular starting material upon treatment with FeCl3, this compound is forming, so which is the major product out of this four. So here this is the correct answer, this option D. And here what is happening, we have seen this in the lecture as well. So here this bond will migrate to here and this will shift. Like first this FeCl3 being a Lewis acid can coordinate with this ketone. So that will form this intermediate. Then this will migrate to here and this will come over here to form this enolate kind of intermediate. So a carbocation is formed at this position. So then what is happening? This TMS group will be leaving to stabilize this carbocation positive charge, and this intermediate will form. Again, it is these are like this is in the enolic form, and when it get tautomerized, it will form this ketone. So the correct answer would be option D. So this starting material will be giving this product upon treatment with this FeCl3. Now, the next question, what is the major product formed in the reaction given below? So, this compound upon treatment with this palladium chloride, copper chloride under oxygen atmosphere, which product would be forming out of this four options given here? And this is a named reaction as well. So, try to identify which reaction it is also. So here the correct answer is this one, option C. So here what is happening, this is an example for Walker process. So in Walker process, this alkene is converted into corresponding methyl ketone. So here as we can see, this is not the corresponding methyl ketone. Here extra double bond is there. This is not the methyl ketone. This is also the cyclized product they have given as option. So the only option is option C. So the detailed mechanism of this Walker process already we have seen in the lecture as well and in the previous tutorial session as well. So I am not going into that detail. So here the correct answer of this question would be option C. Moving to the fifth question, identify the major product formed in the following transformation. So here, this compound upon treatment with this BF3 etherate and DCM, which reaction can happen and which product can be formed in this reaction? So here what is happening? First, this ketone can coordinate with this BF3 etherate. So BF3 etherate is basically a Lewis acid. So this ketone will coordinate with this BF3 etherate. And then what is happening? This double bond will attack over this electron deficient, this carbonyl carbon center, and So this BF3 first coordinate with this ketone, and then this double bond is attacking over this carbonyl carbon center to form this intermediate with a carbocation at the center. Then in order to stabilize that carbocation, this proton will eliminate, and that will result in a double bond over this position. So the correct answer of this question would be option A. So I hope this mechanism is clear. First, BF3 iterate being a Lewis acid will coordinate with the oxygen. Then what is happening? This double bond will attack over that oxygen carbonyl center, and then the carbocation will be stabilized by the elimination loss of one proton to give an alkene over there. So that will give this 5 5 5 fused kind of system. Now, moving to the next question, identify the major product formed in the pyrolysis reaction. So, this question we have already discussed in the tutorial session. So, try to identify the major product which will be formed from this dione when it is heating. So here what is happening, this pyrolysis means this four membered ring is getting pyrolyzed, that is it is breaking and forming this diene, and then this can be redrawn into this structure. So pyrolysis means basically this four membered ring is converting, it is breaking and this alkene dialkene is forming. Now the next question, identify the major product formed in the reaction given below. So this allylic alcohol upon treatment with this triethyl ortho like triethyl ester kind of derivative and catalytic amount of this propanoic acid, which will be the major product, and under heating condition which product can be formed. So here the correct answer of this question is option A. And what is happening here is, so first with this ester and this propanoic acid, this kind of this O allylation is taking place to get this intermediate, and upon heating a 3,3 sigmatropic rearrangement would be happening, and it will give this product. So the correct answer would be option A. So this is an example for Johnson-Clayton rearrangement. So this is getting protonated to form this intermediate, and then this will form. So this alcohol will attack over the center, and that will form this intermediate. Then again, heating this rearrangement will happen to form this alpha beta gamma delta unsaturated system. So this is an example for Johnson-Clayton rearrangement. Now the next question, identify the major product in the following transformation. So this compound upon treatment with this homoallyl grignard and ceric chloride, then hydrolysis, which will be the major product here. So here what is happening, first this 1 4 addition is happening at this position to form here this homoallyl group will come, and then what is happening, this enol ether would be hydrolyzed to get this product. That is, I will draw the intermediate, then it would be easier for you to understand. So in the first step what would be forming, here OMe, it's not 1 for addition actually. So here in the first step, yeah, we are not using any copper or anything, so 1 2 addition is happening. This is OH, and here this 1 2 3 4 1 2 3 4, this is forming, and here this double bond is there, here bromide is there, and here OM is there. So in the next step, this methoxy group will get protonated, and this will shift over here, and this will leave as methanol, and this will come over here, and this alcohol will get eliminated, so that we will get this option A as the major product. Now the next question, identify the major product of the following reaction. So this compound upon treatment with this molybdenum hexacarbonyl and DMSO at 100 degrees Celsius, which will be the major product. So this is an example for Poisson reaction. So in the previous tutorial session, we have seen the mechanism of Poisson reaction. So the correct answer is option B. This would be the major product here. Now the last question, this identify the major product. So this compound upon treatment with this TMS iodide, which will be the major product formed here in this reaction. So here the correct answer is option B. And what is happening? First, this TMS will coordinate with one of this ketone, and the cyclobutane ring will open. This bond will shift over here, and this will come and stabilize this positive charge on oxygen to form this carbocation, which will be quenched by the I minus from TMS iodide to form this product. Then again, this will eliminate, this TMS iodide will eliminate to form this product, and then isomerization of this double bond would happen to form the more stable alpha beta unsaturated compound to get this option B as the major product. So that's all about the week 4 assignment. So with this, we will be concluding today's session. So in the next session, we will discuss firstly about the week 6 lecture contents, and then we will discuss some of the reactions related to the week 6 lecture, and then we will see this week 5 assignment as well in the next tutorial session. So thank you for joining. If you have any doubts, please let me know. See you in the next tutorial session. Thank you.